Hey everyone, I'm Hannah. I'm a postdoc at Georgia Tech. I want to thank the organizers for um, making this conference happen. I'm looking forward to watching all the talks and hopefully chatting with some of you later in the week. And thanks to Sam for organizing this topic group and inviting me to speak. So before we start talking math, I want to introduce my collaborators. So first I should say this is joint work in progress with Samantha Allen, who I guess you know if you're participating in this session, Kanan Inja, Sungwon Kim, and Benjamin Matthias Rupik. And what I want to tell you about today is some generalization of the classical unknotting number and relations between those invariants and connections with those invariants and general 3- and 4-dimensional topology. Okay. So the classical unknotting number is often defined in terms of crossing changes. So here's a trefoil and I've highlighted a crossing and I'm going to change it. So I'm going to change an overpass to an underpass. And I get something isotopic to an unknot. Right. And so a definition of the unknotting number is the minimum number of crossing changes that you need to change a diagram to a diagram for the unknot. And the problem with this definition is that it might depend on what diagram you choose, how many crossing changes that needs to be. So you need to take a minimum over all the diagrams of K, which just sounds extremely cumbersome. Notation is U of K. And so what we've actually shown is that the unknotting number of the trefoil is at most 1, but it can't be 0 if we believe that the trefoil is not the unknot. Only the unknot has unknotting number 0, kind of by definition. And here's a couple reasons why you might be interested in this invariant. Just generally, it's hard to compute and understand, so it's interesting to try to see kind of how far we've come in our study of low-dimensional topology. What can we answer about this invariant? What can't we? And still a very basic question remains. For example, the connected sum of 2 knots, that's an operation that takes 2 knots and gives me a new knot, and the unknotting number of this connected sum is certainly at most the sum of these 2 unknotting numbers, but it's actually conjectured that this should be equal, and it's proven to be true in lots of cases, but it's just not known in general. And this is something reasonable to expect, that kind of invariants behave nicely under connect sum in general, but it just seems very hard to prove something like this. Another reason you might be interested in this invariant is that it's related to 3- and 4-dimensional manifolds that are related to a given knot. So one example is that the unknotting number gives you an upper bound on the smooth 4 genus of our knot. So that's some 4-dimensional property. And so we talked about this problem of having to take a minimum over all diagrams. There's actually a way around this. So here's a local picture of what's happening at a crossing change. And what I want to argue is that you can do this by doing Dane's surgery on this unknotted curve that I've drawn. So if you're not familiar with that terminology, you can think of it as just taking this unknotted curve. It bounds a disk, this flat disk that goes across it, and that disk intersects our knot in 2 places in this picture. And if I cut along that disk, twist 360 degrees and re-glue, what that does is it introduces a full twist in those strands, And that looks like what I've drawn kind of in the middle here. And depending on kind of if I twisted clockwise or counterclockwise, I'll introduce twists of a particular sign. And the sign that I've chosen is one that kind of cancels with the previous crossing that was there. And so you can see that this middle picture simplifies to this picture where the crossing has changed. And there's a subtlety that generally I want this disk to intersect with my knot algebraically 0 times. And an equivalent way to say that is I want one strand to be going up, one strand to be going down. And it's not hard to guarantee that this happens whenever I want to change a crossing. So that's not a big assumption, but it's useful when we want to talk about relating this invariant to 3- and 4-dimensional topics. Okay, so the point of this slide is that a crossing change can be affected by doing this kind of full twist operation, but also vice versa. So this kind of full twist, you can think of it as a crossing change. Okay, so if crossing changes were not enough for you, here are some more operations that we can do on knots, which most certainly change the isotopy class of the knot. So instead of grabbing 2 strands with our unknot and doing ±1 surgery, we can grab more strands. So here I've grabbed 4 strands, and again, I want this null homologous condition. So I want kind of half the strands going up and half going down. That means that whenever I do this, I should grab an even number of strands. Now when I apply a full twist, it's a bit more complicated what the picture looks like, but you can still imagine I cut along this disc, twist 360 degrees and re-glue. And here's a picture of that. So you can kind of see that this knot has some full twisting going on kind of near the top here. And so if I do this -1 surgery, that'll introduce some more full twisting. And the sign is supposed to guarantee that it's of the opposite sign. So all these twists would cancel, leaving me with the simpler knot, which is actually the unknot. But why limit myself to only doing 1 twist at a time? I could also do, in a particular region, do a twist by 720 degrees or more number of full twists. So instead, I allow myself to twist m times, and I also keep track of the sign. And in terms of Dane's surgery, that's 1/m surgery. So here's a picture of doing that. I have all these twists down near the bottom of this knot, and I claim that if I do this particular surgery, it gets rid of most of them and actually introduces a crossing, an opposite crossing, which really simplifies this picture. And so I just want to emphasize that each of these is a generalization of the next. So if I allow myself to grab more strands, that already encompasses a crossing change as a kind of subcase. And if I allow myself to twist m times, that certainly includes twisting ±1 times as a subcase. So each one is kind of a stronger version of the next. And so it seems obvious that, if I allow myself these more and more general moves, I should be able to get to the unknot faster in some sense. This turns out to be really hard to show. So these 2 examples, if I do this full twist, I only need 1 to get to the unknot, but it turns out that I could actually have gotten to the unknot by just 1 crossing change. So I didn't really gain anything by allowing myself this more general move. And actually the same here. I could have changed one of these crossings up here and unknotted my knot. So, you have to do some work to show that you gain something new here, but your intuition is correct. You will actually, in general, get to an unknot faster if you allow these more general moves. Okay, so we have these moves. This allows us to define generalizations of unknotting numbers. So instead, we can ask for the minimum number of null homologous full twists to move from our knot to the unknot. And now with how we've defined these moves, we don't need to talk about diagrams. And so that's the untwisting number. The surgery description number, that's the minimum number of these more generalized twists. And I do an M twist in a particular region and then possibly an N twist in another region. So I'm allowed to vary this number of twists in different regions. And as we said, these are each kind of stronger generalizations of the next. And so we get this natural inequality between all these invariants. And so a natural question is, you would hope that these are not all the same, otherwise they're not very interesting invariants. So we want a knot where, for example, we know that the unknotting number is not equal to the untwisting number. And these exist. So Canaan found some and proved that the unknotting number is larger than the untwisting number using Haggard-Floer homology. They actually found that these invariants can be arbitrarily different. Okay. So I'm interested in this left inequality. So is there a knot where the surgery description number is different from the untwisting number? And we showed, yes, that's true. In a very specific case, so we showed there's infinitely many knots where the surgery description number is 1 and the untwisting number is 2. So we were only able to show that they could be off by 1, whereas Canaan showed that they could be arbitrarily different in the case of untwisting number and unknotting number. And maybe it's not so surprising that we weren't so far able to distinguish these invariants by very much. We showed that there is a tight relationship between the surgery description number and the untwisting number. So it kind of can't be more different than a factor of 3. But there's still this gap that we're not really sure about. So this second theorem leaves open the possibility that there's a knot with surgery description number 1, but untwisting number could be 3. So for those of you that have been thinking this is just not enough generalization of the unknotting number, here's some more. The unknotting number, we described it as, in terms of crossing changes at first, number of crossing changes we need to get to the unknot. Instead, you could try to get to some other knot, and in particular, you could just ask that the knot has a certain property. And the one we're going to ask for is that the Alexander polynomial is equal to 1. This might seem like a strange thing to ask for. It just means that, in certain algebraic invariants, it looks like the unknot. This condition implies that the knot is topologically sliced. So, if you're familiar with that term, that, might be a reason that you want to try to relate your original knot to a knot which is topologically sliced. And each of the invariants that we already introduced have the same kind of generalization. So these sub A, you can read it as algebraic, unknotting number, algebraic, untwisting number, algebraic, surgery description number. And instead of trying to get to the unknot, we're trying to get to a knot with Alexander polynomial equal to 1. And again, there's very natural inequalities. It's easier to get to a knot with Alexander polynomial 1 than to get to the actual unknot. So we get all these inequalities. And now that I've introduced all these generalizations, I'm going to talk about how some of them relate to four-dimensional questions in topology. So I've been saying the word slice already. This just means that the knot bounds an embedded disk in the four-ball. And you can ask for that embedding to be smooth or topologically locally flat, and I'll just say topologically. And I won't go into the difference too much, but it's a very important distinction. And I already mentioned that the unknotting number is upper bound on the 4 genus. Just to say it briefly, the 4 genus, instead of asking the knot to bound an embedded disk in V4, we're asking it to bound some smooth genus G surface, and we're asking for the minimal G that such a surface exists. Okay, but for these more general invariants, there's a more complicated relationship. So if the untwisting number is n, then our knot, you can say it's smoothly sliced in this more general 4 manifold. So some number of connected sums of CP2s and some number of connected sum with the reverse orientation of CP2, which I'll call CP2 bar. But you can bound that number of summands by the untwisting number. And this, instead of saying slice, I'm saying H slice. This is a homological condition on the slice disk that is important in some applications. I'm not going to emphasize the difference too much, but it's just a stronger statement than being just slice. And when we look at the algebraic version of this invariant, you get a similar statement, but for topologically H slice. And again, the difference between smoothly and topologically is an important distinction. And so kind of the difference between the untwisting number and the algebraic twisting number is, maybe important. And I'll just say that the set of H-slice knots has been used by Manolescu, Marangon, and Picarillo to study exotic smooth structures on certain 4 manifolds, in particular connected sums of CP2s and CP2 bars. So I want to talk about this theorem one more time, but from a 4-dimensional perspective. I didn't mention the surgery description number on the previous slide. And, this invariant, on the face of it, doesn't say a lot about H-sliceness in CP2, CP2s connect some CP2 bars, except if the surgery description number is 1, then you know that your knot is H-slice in just a connect sum of positive CP2 bars or just a connect sum of CP2s. But if the surgery description number is larger than 1, all you're really saying is that your knot is H-slice in some number of CP2s and CP2 bars, and you don't even really have a bound on that number a priori. And that's not really saying anything. Any knot is H-slice in a large enough connect sum of CP2s and CP2 bars. But what our theorem is saying is that since there's this relationship between the surgery description number and the untwisting number, the surgery description number does say a bit more. We do actually bound this number of CP2s and CP2 bars, and it's bounded by 3 times the surgery description number of our knot. Okay, let's bring it back to knot theory if that was if four-dimensional manifolds are a bit outside of your wheelhouse. Just to bring it back to the kind of main questions that I want to focus on, we're asking, is there a knot where the Surrey description number is strictly smaller than the untwisting number? You can also ask whether there's a difference between algebraic Surrey description number and algebraic untwisting number. And in words, what this is asking is, does allowing more twists help you unknot faster or get to something which algebraically is like the unknot faster? Thanks for your attention. I hope I see you in part 2, and that we'll talk later in the week.